Yeah, so this is supposed to be a real focus on the physical oceanography along the continental slope. And because that's of the greatest interest to the geodesists. And I'll talk a bit about our experiment off of New Zealand. First, I wanted to just say we're really honored to have the participation of some really eminent physical oceanography experts in coastal and slope processes, and to kind of facilitate that, because the communities don't know each other yet. And so that there's more discussions start right off at the coffee breaks and the lunches and so on. I was going to ask several of the speakers to actually stand up and give them sort of a 1 minute, more than the introduction that we just went through, and say their particular interests. So I have these listed in the order pretty much of the scheduled speakers. So Chris Hughes would, yeah. Chris is a professor at University of Liverpool, and this is all. These are words from his website, but it's better to have him speak.
So yeah, I've been in Liverpool forever, since 1992 at various different institutes, and always looking at ocean dynamics from a sort of geodetic point of view. So I've always been interested in sea level and ocean bottom pressure and gravity, and how all of those systems interact. I feel as if it's taken me 30 years to move what I should have been able to think of in 2 years, but it always works that way. And gradually discovering more and more coherence in the pressures, and more interesting things about what these pressures on the ocean boundaries tell you about the ocean circulation. Really excited to see what's going on here, and this explosion of interest in the continental slope, because it's exactly what I'm most interested in at the moment.
Thank you, Chris. Yes, and Ken Brink is at Woods Hole Oceanographic, and give him a chance. And let's, yeah.
Okay, Randy asked each of us to come up with 2 slides. One thing I've spent a lot of my career looking at is observations and modeling of coastal upwelling, which is where you have an alongshore wind coming out of the screen in the northern hemisphere, pushing surface waters offshore, and to compensate, you bring up cold water, which is why San Francisco is so cold in the summertime, for example. Also, why you find so many anchovies off Peru. So this is the classic way to look at it, is through measurements across one of these things. Randy, next. And my interest more recently has been in modeling of these features, and this is looking at it from above in a model where you have cold water near the coast and warmer water offshore. And the point is that it's a mess. These things are unstable, they form eddies, all these small features, and I'll be talking more about some of that later on. But I'm personally interested in a wide range of coastal phenomena, so I try not to be easy to label.
Yeah, good. Thanks, Ken. So Alex Kuripov, would you care to stand up? Yeah, sure. So Alex is at NOAA and Oregon State University, and yeah.
Yeah, I think Oregon State University will be a full statement, but I don't know. Still, I'm a course of the faculty of Oregon State. So I think that this everything is correct. So I just follow Cambridge's steps to learn something about the ocean, including coastal pathways and coastal upwelling. And I do this by building models and trying to understand what model outputs I need.
Thank you. Yeah. And now Eleanor Fricke Williams got her airplane schedule completely messed up and is not going to be able to join us, unfortunately. She sent a recorded talk that you'll hear tomorrow. So I will just read the words from her website. She has recently moved to the University of Hamburg as a Frau Doctor Professor. So she uses observations to investigate ocean dynamics and circulation in a changing climate. She has particular interest in problems spanning scales from micro to large scale, or various spheres like biogeosphere, cryosphere, atmosphere, and in methods that leverage traditional observations with new platforms and satellite data. For example, I investigate how the Gulf Stream and the ocean conveyor system redistribute heat around the Atlantic. Rui Ponte is at AER, the Atmosphere and Environmental Research Group, and has wide expertise. Let Rui speak for yourself.
Yes, my interest in bottom pressure goes back maybe more than 30 years, when I was actually looking at the effects of the ocean on Earth rotation. And for that, you need to know what the mass in the ocean is doing and how it's moving around. And that's what got me going with bottom pressure. And then it's very interesting to think of bottom pressure and sea level in conjunction, because if you know both, you can infer things about what a column is doing in terms of density and so on. And that's something that I've worked on for a while too. And most recently, I've been looking at bottom pressure in terms of contributions from atmospheric forcing versus internal variability in the ocean that can drive their own bottom pressure signals, and how those two are sort of interacting and important in many ways. Be happy to continue the conversation.
Great, thank you. Uwe Sand is at Scripps Institution of Oceanography. He actually will arrive, he said, right about noon, be in time for lunch, and he would be willing, if at the end of this, he'd be willing to say something. His list of interests we'll take up later. Karina Ramos Musalem, right, is at Universidad Nacional Autónoma in Mexico, which is Mexico City.
Yeah.
Right.
Very landlocked.
Yeah.
I'm Karina Ramos Musalem. I am an assistant professor at the National University of Mexico. Fairly recent. I got my PhD in 2020. And I guess like all PhDs, I feel like I know some like very specific things about flow over topography problems, specifically somewhere in canyons and how they affect the dynamics of currents on the shelf. But I am interested in all kinds of flow over topography problems. Now I work in an atmospheric sciences institute, so I'm trying to do both in the atmosphere and in the ocean. But I think that I'm particularly interested in problems that, or the ocean dynamics that facilitate cross-shelf exchanges between the deep ocean and the coastal regions. And I don't know, I know nothing about bottom pressure, but I'm interested specifically for this, right, for the signature that these physical or ocean processes have on bottom pressure. And I'm also bringing the interest of people that I work with that do numerical models and how, I mean, bottom pressure data can help us with adjoint models and really data simulation, right? Not my expertise, but I need to bring their message. So that's right.
Great. Thank you, Karina. And now Richard Ray, I listed him here. He's not actually giving one of the longer talks, but he's such a guru of tides of all kinds in the world that I just wanted him to speak.
Yeah. Okay. So I use bottom pressure to study tides. Of course, I wish I realized you were taking some slides if I can.
Oh,
because I have a great picture of the spectrum of in the tidal band of like 1, 2, 3 cycles a day of what you would see in a tide gauge, like a place in Nantucket, and then compare that spectrum to what a bottom pressure sees. And I have a DART station about 200 kilometers away from the Antarctic. And if you look at those two spectra, the tide peaks are the same, but the background noise is terrifically reduced in the bottom pressure as compared to the surface tide gauge. So you saw there people who are complaining about all the water noise. You haven't seen anything unless you're looking at the surface. So the noise is terrifically larger there. So I really want to see the bottom pressure data. With that low noise, you can look at fine details of the type of spectrum there. And I really like to then compare what a bottom pressure sees, bottom pressure sensor sees to what an altimeter sees. Because there, you have to deal with all kinds of complications, and it's rather interdisciplinary, in fact, because an altimeter sees the ocean surface tide. It also sees the solid earth tide, both the body tide and long scale driven by the gravitational potential. It also sees the effect of that water mass loading solid earth, so it sees the low tide as well. And of course, the bottom pressure sees not only the ocean tide, it sees the air tide. So you have to take into account all these different aspects. Makes it very interesting.
Yep, thank you. Right. There would certainly be an opportunity to put your slide into one of the slides into
Okay.
one of the lightning talks, for instance.
Okay.
Yeah, right. Let's see. So okay, so we'll go to my talk. So physical oceanography along continental slope. And I wanted to mention, Matt and I have money for a postdoc that we want to hire later this year in probably favoring physical oceanography to do the kind of things that I'm going to be talking about. But so put that word out and let me know. The first thing that I'm going to talk about is probably quite familiar to all of you. It's hydrostatic balance, but we'll just take a look at the background of it. It's that let's see if I can find my, here we go. Goodness. Oopsie. Yeah, the thing is, people watching online can't see this pointer. So if I can get this thing to work. The place, it's going to keep jumping on me though. The situation in which hydrostatic balance applies is when the acceleration terms in this equation are negligible. And that is the case for long waves, where long compared to the depth of the water, and long periods. And then one can integrate that expression here, and for many purposes, it's adequate to use a kind of standard ocean expression of pressure as a function of z and latitude. See, this keeps jumping. Oopsie. Sorry. And there's the pointer again. Has a latitude dependence because of the dependence of g on latitude. The other thing, very quickly, is that the units in SI units of pressure are pascals. It's convenient for me to think about hectopascals. Oops, sorry. I may not, this jumpiness may spoil it, but 100 pascals or hectopascal is about the depth of 1 centimeter of seawater. Oopsie. So the horizontal balance, we're going to look at a little more carefully. It's geostrophic. And what does that mean? So again, where's my pointer? There we go. So again, in the horizontal balance is the accelerations, the Coriolis term, and pressure gradient being the main terms. And rather non-intuitively, this Coriolis term in large scale, low frequency flow in the ocean is the dominant one. Doesn't affect your personal life at all. when you throw a baseball or something like that. But it's absolutely dominant in for large scale, low frequency currents in the ocean. And so, and how we measure that is take the ratio of one of, say, this nonlinear acceleration term to the Coriolis term down here. And that ratio, U over FL, is the Rossby number. When the Rossby number is small, it says that the Coriolis term is the main one. And so what we have, and for the kinds of scales that we're dealing with along the coastal ocean, say longer than 20 kilometers and longer periods than about 3 days, you end up with Rossby number of about 0.05 and actually a very good geostrophic balance. I'll talk a little bit later at the end about the next most important term, which is curvature. But in any case, what the interpretation of this is that the lateral gradient pressure is proportional to the current speed, and that current flows along isobars, not across, not down the pressure gradient. So, and a familiar example of that is this with weather in the atmosphere and in the ocean. So we're familiar with low and high pressure centers in the atmosphere, and the flow goes along these isobars. It goes counterclockwise in the northern hemisphere, and similarly in the ocean, we had an experiment under the Kuroshio extension off to the east of Japan. And this was a map of bottom pressures and currents that were measured there. And here was a low pressure center. You see the flow is around counterclockwise around that low. It's basically along these isobars. It's fast where the gradient is high and slower where the gradient is low. So the experiment that Matt already mentioned off of New Zealand that Spar Webb and Laura Wallace were involved in 2014 and 15. It's called Hobbits. Oopsie. And this example of a dozen pressure records are plotted in black here. And these pressure records are compared against the HICOM model, the global HICOM model, and a ROMS, a regional ocean model system, in the blue and the red. And what you see in here is that they're very, very similar. As Matt's terminology was, the models are realistic. But when you take the differences between the model and the, let's see if I can get my pointer showing up again here. All this pointer stuff is trying to help people if they're following it online. But in any case, the differences between the observations and the model are still almost 2/3 as big as the original signal that's there. So you win, but you win slowly by subtracting, by using the models to subtract it. This will be useful information. It's the HICOM, which is realistic, shows the kind of currents that are measured along the New Zealand coast here. You see, and the red arrows there's sort of a mean current to the south. Oops. And the ellipses are standard deviation ellipses showing that the longshore component of current here is something like, what do I say, tenth of a meter per second, 10 centimeters per second. In the variability, length of those lines is about twice the red scale up there. And can't find the pointer. Where'd it go? Sorry. So, and then the cross slope speed is about 5 times slower. And the lateral scale along here is set by the width of the continental slope. It's about 50 kilometers. But it does have important changes along this slope there. Along this. We'll talk about that. This is an analysis of those C4 pressures. They're all plotted on top of each other in the top plot, and I think, let's see, here we go. I can see that. No, I can see my pointer. So the sites are very similar. It's doing spectra and complex EOF analysis of these data. The complex EOF allows you to measure the amplitude and the phase in case that there's phase differences from one site to another. And so the spectral peaks are shown here in a variance conserving plot of log frequency versus variance. And what's interesting is that we see peaks at 16 days, 8 days, and 6 to 5 days. They've been, of course, we've removed the tides. They're three-day low pass filtering. What we have, the arrangement of the plots, the bluish colors are the shallow ones, the green in the middle a bit higher, and then these orange, red, and violet are the ones that are grouped offshore. So I don't fully understand why this is the case, but at the 16-day period, they really sort themselves out, with the offshore being more energetic than these onshore. Well, they're not real close onshore, 700 to 900 meter deep. The CEOF modes are plotted down here at the bottom, and so each of them has an amplitude and a phase, and they're listed along here from onshore to offshore. So the lowest mode, the lowest mode is very uniform in amplitude and very uniform in phase across this array of a dozen sites that have us. They span some 100 or so kilometers along shore and 70 across, something like that. And the point. So the second mode is sort of, oh man, is interesting in that it has a high near shore. It goes down to very low in these middle depths, and then oops, the thing keeps dropping. There we go. Wonderful. Unless I move it, and then the amplitude gets higher again as you proceed offshore. However, those amplitudes are associated with a change in sign, basically, because the onshore phase, which is near zero, is then offshore. It's 180 degrees offset for whether you're here or here. So mode 2 flips its sign and has a zero crossing near 1600 meters across there, and that's pretty similar to what we saw off of Oregon, off Cascadia, in the experiment that Matt showed as our pilot experiment. The energy or the variance is 89%, 6%, and then mode 3 sort of barely detectable and high among the other modes. Here's another way of looking at those, at the modes plotted, projected back as time series. And so all of the pressures are plotted on top of each other here. They projected onto mode 1 in this second panel, which has the 89% of the variance, and they look almost completely the same. Mode 2, it really illustrates this change in the flip in sign from what are the nearer shore and further, or I guess these are the near shore and these are the offshore sites. And then in the middle, almost zero signal. So that, here we go. So that's why I've tentatively I've called them close to coastal trapped waves. And so the coastal trapped waves are a very useful way to think about these the dominant variability along the coast here. It's the idealization for it start out, well, it's for long periods compared to the inertial period. So in the red box first. And continuously stratified ocean, which is significant. All the modes of coastal trapped waves propagate along the continental slope and shelf, and the coast is on the right in the northern hemisphere. Coast is on the left in the southern hemisphere. The phase speeds resemble the lowest mode resemble internal Kelvin waves, which are fast and long and produce long wavelengths compared to, say, mid-ocean eddies offshore. In terms of the phase speed, the cross slope scale of coastal trapped waves tends to be set by the topographic bottom topography scale, and the fact when you set up the differential equations that conform to these points on the top there, the sidewall boundary conditions give you a set of modes which decay offshore, and the cross stream structure has then a set of nodes and antinodes, more and more complicated as you go to higher modes. And the higher modes propagate slower, often like 1 over n. The nth mode is about half. The second mode is about half as fast as the first, for instance. So because they dissipate faster, the first couple of modes carry most of the variance, and they are driven by perturbations that have happened upstream of where you're working, because they're all the propagation, for instance, along New Zealand is with the coast to the left. It's in the southern hemisphere. So those modes that we're talking about are moving through the north towards the equator. And they've been driven by things that have hit the coast further to the south. Wind setup, atmospheric pressure setup, and incoming offshore eddies. And then I put in slightly smaller print here, something I've gleaned or condensed these set of properties from, there's really a wide literature on coastal trapped waves. And Ken Brink has been very much in the middle of that, of publications about that. I just listed one of his more recent summarizing things here at the bottom. The thing that where did I get this? See, I'm not so sure about is the vertical, the vertical structure. The lowest mode is almost definitely fairly uniform with depth. The higher modes, different models and different assumptions give slightly different results, but they tend to be bottom intensified and lean a little bit offshore, kind of normal to the topography rather than just straight vertical. And right, I'm interested to learn here about to other experts about that. So if we compare that to what we see off of New Zealand, right, so we have nice low frequencies. They we're actually not able to. They propagate so fast through that north-south array that we can't detect the phase lags. So I'm going with more generic sorts of numbers. The first mode propagates at about 1 meter per second, something like 100 kilometers in a day. Second mode would be about half of that. What do I have here? Oh, right. And so that would give a longshore, calculate a longshore wavelengths that would be 400 to 1600 kilometers. Which, and I put a question mark because then, I mean, the North and South Island of New Zealand broken up by the Hook Passage between Wellington must be pretty complicated. What drives them, actually. So we have that, but the cross slope scale is something like 50 kilometers. And then I wanted to just bear in mind that all that I've said about coastal traffic waves is an idealization, that the coast is perfectly straight coastline, and there's no valleys and ridges that you would come across, and there's no narrowing and wider sections of the slope as you go along there, and the topographic slope is monotonic, and because the slope is large, we can usually get away with constant F assumption. But so they're very useful concepts. Now I'm going to talk about two applications of geostrophy, which will apply to what the different physical oceanographers, and speaking in the next couple days, how they use it. One is they use pressures to determine currents, and the other is we'll use currents to determine pressures. So for an example, if you integrate the velocity across a transect, such as perhaps all the way across the North Atlantic, as an example, you could integrate up this transport per unit depth by integrating velocity across from A to B across the Atlantic, and that would be this integral of the geostrophic expression, which comes out, because that's a nice exact integral. You just, all you need to know is PB minus PA. You need to know the pressures on the two sides of the Atlantic. So it looks very simple to get the transport per unit depth here, except you'll talk, the two pressures have to be known absolutely to something like a centimeter. And that's a real challenge, which people are, it's very attractive to do that compared to putting current meters every few kilometers across the entire Atlantic. Another application now that I'm going to talk about mainly is using currents to determine the pressure fields. So we just turn this, rearrange this expression. And if you can resolve the velocities in a correlated way, you can do this integral observationally and find that the pressure at some site X that you want is relative to a reference is found by integrating up the velocities across there. So that's where we're going. And in fact, you can do it in 2 dimensions. And I'll do it with a method called optimal interpolation. So, but first, yeah, is that one? Yeah, first, bear with me. This is a grungy set of estimates that we have to pay. It's important. We have to pay attention to. So we're going to estimate the current strength for mode 1, the current strength for mode 2, the 2 modes that I just showed you that we found off of northern New Zealand, and then conversely, we'll estimate how much pressure difference there could be across mode 2. So first, so if we just do the geostrophic estimate for the velocity of mode 1 from the pressure gradient, well, the pressure gradient is actually much less than 10% of that signal. The RMS signal, or the standard deviation signal was observed there was about 2.6 hectopascals. So that's the whole signal, aside from the tides, and in the distance of 70 kilometers. So if we put that into our geostrophic calculation, turn out all the numbers, go through them, you get the standard deviation of that first mode is something like 0.3 centimeters per second. It's really weak, basically below noise. So mode 1 has very, very little velocity signal associated with it. Here's the thing that kind of blew my socks off in a way. Mode 2, although it only has 6% of the variance, that's 24%, 25% of the amplitude of mode 1, and it has a lot shorter scales because we saw that it went through that 0 crossing. So if we put in the similar numbers for that and account for this narrowness of the 0 crossing, which gives a horizontal scale of about 11 kilometers, we get a velocity for mode 2 of about 11 centimeters per second. 35 times bigger. So that's pretty amazing. I think it's also one of the reasons that those higher modes dissipate faster, is that they've got a lot more bottom velocity rubbing against the bottom. This thing keeps jumping. Conversely, what we're going to do is use those velocities to estimate pressure differences, and this just kind of turns the same numbers around the other way. I said, well, if we had a horizontal scale of in that case, 20 kilometers, and we look at the standard deviation in all those variance ellipses was around 10 centimeters per second, put in the numbers, and you get 2 hectopascals. So across, accounting for the fact that that mode 2 changes sign, so you get a factor of 2 of amplitude, you get a very sizable pressure difference across a jet. It's comparable to the signal that we see when mode 1 is all subtracted out. So we know we have a reasonable sized mode 2 signal to deal with, and so then to do optimal interpolation, which is a very practical way of estimating the currents from the velocities, we need to use multivariate correlation functions. So here, this took a set of observations along the New Zealand coast, and first of all, for a set of pressures, these are from a model. At sites along the coast, you get these correlations. Are they big enough to show up? I hope to people in the back. They basically, the correlation curve comes down here, and they have a correlation scale of about 70 kilometers along a long slope. That's that, and that's after these. Oh, and I should say we've removed the common mode among all those sites, because the common mode was almost the same all throughout that array. So after removing that, these are the correlations, have about a 70 kilometer long slope scale.
Randy, that's the longshore component of current.
No, this is the pressure.
Oh,
These are the pressures. Yeah, that's fine. Yeah. So so they have that scale. The cross slope pressures have correlations that go down, go through a zero at about 17 kilometers and continue quite significant offshore. So it suggests that the correlation length offshore is, well, at least 50 to 70 kilometers. But they have this zero crossing at about 17. So if we then take that same information and make a correlation function that has different has the appropriate longshore, cross shore, and zero crossing scales to it, this is what the pressure to pressure correlation function looks like. It's long in the longshore direction and has this zero crossing with the high to the left, because we're in the southern hemisphere there. And then if we, let's see, so I didn't quite mean to leave that. So that's what the pressure to pressure correlation function looks like. And then if we add in the geostrophic calculation for non-divergent geostrophic correlation functions, the pressure to longshore velocity and pressure to cross-shore velocity. So here's the longshore and cross-shore, and those correlation scales we see are higher with currents, higher pressure when the current is to the left of the current, for instance, and again higher pressure to the left of this current, but much weaker. So those, one of the big attractions or advantages of using optimal interpolation is that you can estimate the error maps ahead of time and design your array, design your measurement array. And so I've done that here and in two extreme examples. One is, what if we only used reference sites for mode 2 in particular that are offshore of the trench, because those reference sites shouldn't move vertically. All the other sites, all the other sites that you want to measure here might be affected by a slow slip event. It might have their own signal to it. You don't want that signal to contaminate the estimate of the ocean signal. You've got to take the ocean signal out clean. And the currents for slow slip events, deep currents, are not going to be affected by a little bit of change in seafloor depth, centimeters of change. So so if you just use the offshore pressures, basically for mode 2, it really can't help you much. But if you instead use only the offshore pressures in this right-hand plot, and all of the currents at all the sites, because they're not going to be contaminated by the slow slip event, then you get a much bigger, nice, clean, low variance, low error map estimated there. So let's see. Right. So most of this array with that kind of spacing of instruments, which is pretty short spacing compared to the correlation scale. So there's a lot of correlated pressures going in there that helps you reduce the error estimates by averaging. So that's the That's the real story and how we designed that array. And then I thought that here at the end, I would just take a couple of words as well. What can possibly go wrong? So because this estimate is one that, well, it has estimated a noise level in the pressure measurements. And it gets mapping errors just because you're not perfectly resolving the field. But one of the biggest things I think that can happen is that smaller scales that in this geostrophic balance, actually the next acceleration term that is most important is a centripetal term, which is the u squared over r. And that then I've made here an estimate of what sort of R you might see. The models found are probably a bit of a guide, but they have limited resolution. So I made a sort of an estimate, said if you're 50 meters above the bottom, which is where our current meters were, that the smallest curvature of eddies that are going to go by there, if the Burger number is of order 1, that's the thing to discuss with people who are more expert than me. It says that the scale would be about 5 kilometers. In other words, you'd have eddies bigger than that, up at 50 meters off the bottom, larger diameter. If you do that, you get a Rossby number of about 0.2. And that would go into this balance here. So that's suggesting that this is introducing something like 20%, noise into the geostrophic pressures. That's noise amplitude. And so that's a suggestion of one thing that could make it more complicated. I'll talk privately with people of how we might address this without having to have an array every 5 kilometers or less out there. By taking advantage of knowledge of the seafloor topography, which is quite well resolved. And then other things, I know up on the shelf where you have higher tidal currents, you also get you get form drag kind of terms that give you u squared over r kind of errors and noise to them. So this is my summary about for how we designed and lesson learned, and I think fairly widely apply to other coastal slope regions. So the mapped geostrophic pressures unaffected by source of events, a correlated array of current measurements produces the smallest residual pressures compared to just offshore sites. If you have longshore sites, since I didn't say that, but the longshore pressure sites are going to be very helpful in addressing that mode 1 variability. And so, but this focus is on taking out the mode 2, getting just beyond that, and then if the reference sites have AZA minimizing the reference pressure drift, then the currents will carry that all to the entire array inshore. So it'll help to move drift to all the sites. Yes, and right, and then having multiple current sites and transects even within these correlation lengths help average out the non-geostrophic signals that are in there. And then there's just a reminder that the real topography is complicated. It's not a straight, long, straight coast. It has valleys and ridges. It introduced big curves. It has places where the slope was 30 kilometers wide, and other places where it was 70 kilometers wide or more, just along that section of New Zealand. So surely even mode 1 has to follow that to some extent. And a smart thing to do probably is to put sensors, reference sensors at comparable depths across that to get rid of mode 1 the best you can. So I think a big point is that there's going to be non-geostrophic small scale signals in there that I cannot think of any way for you to get rid of, any practical way, by having, you know, a gajillion current measurements in there. So there's going to be probably some non-linear processes that are going to keep some noise. Hopefully, I would say less than 1 centimeter, one hectopascal RMS, maybe 0.8, something like that. But I can't see getting down to 0.5, for instance. So we have in this design, we have sites to the south, to the north, allegedly places where they're not going to have slow slip events affecting the bottom height at the same time that the ones in the middle do. So there's good reference for the mode 1 moving along the coast, and we have nice reference sites for them offshore. Some of those are A0A type of sensors, and then the current meters will carry that set of pressure estimates for both modes in short. So that's what I have to say.